Look up at the night sky, and it is easy to assume you are looking at a perfect, eternal machine. We think of the planets, their moons, and our own artificial satellites as moving along permanent, predictable tracks. But every rotation is a subtle battle against energy loss. Even in the deep silence of space, a planet's pull is constantly working to reclaim the objects circling it. This is a process called orbital decay. Whether it is through physical friction or the complex tug-of-war of gravity, the universe is steadily stealing kinetic energy from orbiting bodies, pulling them downward. Right now, a slow-motion death spiral is claiming everything from satellites in low Earth orbit to small moons like Mars's Phobos and Jupiter's Adrastea. One eventually yields to the gravity it spent billions of years trying to escape. To understand how this works, we can start close to home, in low Earth orbit. We often imagine that once a satellite reaches space, it has entered a perfect vacuum. Space is incredibly empty, but at altitudes of a few hundred kilometers, Earth's upper atmosphere is still present. It acts like a very thin fluid, creating a continuous atmospheric drag that pushes against anything moving through it. A satellite's physical shape determines how fast it falls. A heavy spacecraft with a small profile will push through this resistance fairly well, but an object with a wide cross-section acts like a parachute, rapidly bleeding off forward velocity with every atmospheric collision. And orbital decay compounds on itself. As a satellite loses speed, its altitude drops. That lower altitude means traveling through a denser layer of the atmosphere, which generates even more drag, stripping away energy faster and faster until the object burns up entirely. Our entire multi-billion-dollar communications and observation infrastructure sits in this friction zone. For every piece of hardware we place in low Earth orbit, a fiery re-entry is a mathematical certainty. But atmospheric drag only extends so far. Out in the deep vacuum of the outer solar system, there is no air to slow things down. So why are moons like Adrastea and Triton also falling toward their host planets? The culprit here is tidal friction. When a moon orbits a planet faster than that planet rotates on its axis, or when it orbits backward against the planet's rotation, it creates a gravitational mismatch. The host planet constantly pulls back on the moon, quietly draining its momentum over billions of years. These massive moons do not burn up in an atmosphere. Long before they can reach the planet's surface, they hit a fatal boundary known as the Roche limit. Every celestial body is held together by its own internal gravity. But as a moon gets closer to its host planet, the tidal forces pulling on its near side become significantly stronger than the forces on its far side. The Roche limit is the exact distance where the planet's pulling force overpowers the moon's internal gravity and physically stretches and shreds the moon to pieces. We have watched this physics in action. In 1992, a comet named Shoemaker-Levy 9 wandered inside Jupiter's Roche limit. The massive planet's gravity cleanly ripped the comet into a string of glowing fragments before they plunged into the atmosphere. This mathematical threshold guarantees that falling celestial bodies rarely make it to the ground intact. They are dismantled in the void. When a moon is torn apart, the material does not simply vanish. The shredded rock and ice disperse along the orbital path, spreading out to form planetary rings. Jupiter's main ring sits directly at the orbit of its moon Adrastea. Because the moon is actively being pelted by meteorites and its low gravity cannot hold on to the ejecta, it constantly bleeds material out into space to feed the ring around it. We know exactly which moons are next. Mars's moon Phobos is highly irregular and loosely bound, closer to a rubble pile than a solid sphere. Orbiting just a few thousand miles above the Martian surface, it is expected to cross the Roche limit in roughly 70 million years. Researchers project that Phobos will disintegrate and form a rocky ring around Mars. Over time, that ring debris will clump back together to form a new, smaller moon, which will eventually decay, hit the limit, and be shredded all over again. 3.5 billion years from now, Neptune's largest moon, Triton, will meet the same fate. When a frozen world slightly larger than Pluto is finally dragged across its Roche limit, the resulting debris will create a spectacular ring system that rivals Saturn's. These rings are active tombstones, marking the exact sites where orbiting worlds finally collapsed. They reveal a solar system that functions as a violent, beautiful recycling engine.